Hello, geometry scholars! Today we're going to be continuing our work with angle pair relationships by looking at a couple of proofs. Before we begin, please make sure you have your notes and something to write with so that you can follow along with the video as we go. You're not going to need a calculator today. If at any time the video goes too fast and you miss something, feel free to pause, rewind, and rewatch anything you may have missed. And with that, let's go ahead and get started with some of these proofs about angle pair relationships. Now, our first proof is actually going to prove one of our theorems from this section. It is the right angles congruence theorem. Now, it is important to note before we begin our proof that we cannot use this theorem as a reason in this proof. Consider defining a word. If you're defining a word for someone and telling them what it means, you're not going to use that word in the definition. They don't know what the word means, so using the word as part of its definition is not going to be helpful. The same logic follows when we write a proof. If we're trying to prove that a theorem is true, we can't use that theorem to validate the theorem. We've got to use other theorems, other postulates, other definitions to show that this is true. All right, now that we've established we can't use this, let's consider what we can use. The theorem itself says that if we have two right angles, so angle 1 and angle 2 are right angles, then those angles must be congruent. Well, we start our proof just like we start any other proof. Let's start with the fact that those two angles are in fact right angles. Well, if we have right angles, what does that tell us? What conclusion can we make from this given statement? Well, I don't know about you, but I know what a right angle is, and I think you do too. A right angle is an angle that has a 90-degree measurement. So let's say that each angle, angle 1 and 2, have 90-degree measurements. And we make that conclusion based on what we know about right angles. We make our conclusion based on our definition of right angles. Consider our goal. We want our angles to be congruent. Right now, each angle has a total of 90 degrees. If we want them to be congruent, we want them to be the same. Well, if they're both equal to 90, they are the same. So we're almost to our goal. We can in fact say that our angles are equal in measure. Each angle equals 90, so each angle equals each other. We can use either our transitive property or the substitution property to make this conclusion, depending upon how you think about it. Transitive says two angles equal to the same measure have to equal each other. As opposed to substitution, where we consider making a replacement. I can replace this 90 degrees with the angle 2, because I know angle 2 is actually equal to 90 degrees. So if I consider a replacement, the replacement idea is substitution. All right, now that our angles are equal, we are there, guys. We know our angles are congruent. We can change that equality into a congruence using our definition of congruence, or more specifically in this case, our definition of congruent angles. One proof down, guys. 3 to go. Example number 6 asks us to prove the vertical angles congruence theorem. Now, before we begin our proof, what is the one theorem we cannot use as a reason in this proof? Hopefully you said we cannot use vertical angles congruence theorem as a reason. Remember, when proving a theorem, we cannot use that theorem in the proof. All right, let's see what we know and let's see what theorems we can use. The vertical angles congruence theorem says that if two angles are vertical, which in this case, angles 5 and 7 are vertical, then we can say that the angles are congruent. So we want to prove that that statement is true without using the vertical angles congruence theorem. All right, starting off where we always start, which is our given information. We know that we have vertical angles. Now, unfortunately, this statement doesn't give us much of a conclusion. In the last proof, we had a nice direct conclusion we could make from our given statement, but the fact that we have vertical angles doesn't tell us much. The only thing we could say is that they're congruent, but that would use our theorem. So we can't jump to the congruence yet. Since our given statement does not tell us much, let's look to our diagram and see what conclusions we can get from there. Looking at my diagram, I see a couple of things. I see that angle 5 and 6 are a linear pair. Their total should be 180. The same is true of angles 6 and 7. Their total should be 180. So let's use that as our next statement in the proof. Let's say the measure of angle 5 plus the measure of angle 6 equals 180. As well, the measure of angle 6 plus the measure of angle 7 equals 180. We know that because the diagram shows us they are linear pairs. So we're applying our linear pair postulate. Now we should be able to make a conclusion from our statements. Look carefully. 5 and 6 equal 180. 6 and 7 equal 180. Both of our sums equal 180. So what does that tell us about both of our sums? It tells us that our sums are equal to each other. So once again, we can apply our transitive property or substitution here to make our conclusion. To figure out what we need to do next, let's again look to our proof statement. Our goal is to get 5 and 7 to be the same. Looking at our equation, we have 5 and 7 here. The only thing that's in the way of getting them to be equal is angle 6. If we can eliminate angle 6, we can get 5 and 7 to be the same. How could we eliminate angle 6? We've done this a couple times now, guys. Let's say angle 6 is equal to itself. That's our reflexive property. Doing so will allow us to cancel out angle 6 on both sides, leaving us with just angle 5 and 7 remaining in the equation. But what rule are we using here to cancel out the angles? Did you remember the subtraction property? If we subtract line 4 from line 3, the 6's cancel, and we're left with the angles we're looking for. Now we do need to add one more line to this proof. We're not quite there. Our goal is to say that our angles are congruent. Right now we have that our angles are equal. So what do we need to do to change equality into congruence? If you're not sure, check back at the last proof. We used it there. Did you find it? Did you find the definition of congruent angles? If you did, you got it right. All right, folks, example 7. Let's continue. The congruent supplements theorem. This is one of the tougher ones in this section. This is the theorem that says if we have two angles, 1 and 3, that are supplementary to the same angle, angle 2, then those two angles, 1 and 3, have to be congruent to each other. So that's our goal here. We know that these two are supplements and these two are supplements. Since they have a supplement in common, we want to prove that these two angles are in fact congruent. All right, guys, let's give it a try. Also remembering that we cannot use this theorem as a reason in our proof. Given information, we've got lots of supplements going on, so let's get them all down in our first line. 1 and 2 are supplements, as well 3 and 2 are supplements. Well, what do you know about supplementary angles? Hopefully you remember, and I think you do. Supplementary angles have a total of 180. So let's make that our next conclusion. Let's say each one of these pairs has a total of 180 degrees. Now in the last proof we used linear pair postulate, but notice these aren't in fact linear pairs. They're not connected, they're not adjacent. But we do know that they're supplements from our given information, so we're just going to say definition of supplementary angles here, as opposed to our linear pair postulate. Other than this reason being different, our steps are starting to look very similar to what we did in the last proof. We've got two sets of angles that are equal to 180. We had this in the last proof. So what do you think we should do next? Let's set them equal to each other, guys. Again, transitive or substitution would be appropriate here. Let's look back to our goal one more time. We want 1 and 3 to be the same. Looking at our equation, we have 1 and 3 on both sides of this equation. The only thing that's in the way here is angle 2. So if we can eliminate angle 2, we can get 1 and 3 to be the same. So let's follow the same steps we did in the previous proof. Take a moment, pause the video, give it a try. Can you finish it from here? Pause it now and try it. All right, folks, you've had a moment to pause and to think. Let's see how you did. In the next line, let's say angle 2 is equal to itself. Again, that's our reflexive property. Doing so will allow us to cancel out our angles and leave us with the 2 we're looking for, which is angle 1 and angle 3 being equal in measure. Now our goal here is not equality. Once again, our goal here is congruence. So we need to take one more step, change our equality into a congruent statement using our definition of congruence. All right, folks, there's just one more proof remaining, and I'm going to let this one up to you. Notice our given statement says that angles 1 and 4 are the same. Our goal is to show that 2 and 3 are the same. Look back at the previous proofs we've done today. Think about what you can do to get 2 and 3 to be the same. Do take note of some of the items found in the diagram. Notice something about angles 1 and 2. What can you see here to be true? Same goes with 3 and 4. What can you see here to be true? So use your given information, use your diagram, see if you can complete this proof. When you are finished, be sure to check your answer with the answer key. After you've done that, you are finished with your notes for today.